All right, this is an exciting continuation of our problem to the moon. So once again, suppose you put $100 in a savings account that pays interest at an annual rate of 5% compounded continuously. And we've seen last time that it would take 18 years for your savings to reach $250. But now, what if we put in a little twist and also contribute $10 a year, compounded continuously? Meaning, like every second, we put a portion of those $10 into the account. Of course, it'll go faster, but now let's say how much faster. So, how long will it take in this case for your savings to reach $250? And the idea is the same thing. So, we just do a little change in time. So derivation, so h, once again, a small change in time. In this case, well, same as before, your savings, so in h time, I think you had it in years, h years, your savings will change or increase, in this case, of course, by, well, the stuff we had before was 0.0.5 h s of t. That was from before. Then 5%, small increment, depends on how much saving you have. But now, because you're also contributing, there's an extra small change. Of course, since you're putting a little bit of money at every step, it depends on age. And since you're contributing $10, it should depend on 10. But this time, this new term does not depend on how much savings you have. Because think about it, if you have $1,000 or 10 or like $1 million, you would still contribute just part of the $10. That's constant. So, yeah. And so the only change to our equation is we still have s of t plus h minus s of t. So 0.05 h s of t plus 10h. And then once again, writing this as a difference quotient, we get s of t plus h minus s of t over h is 0.05 h, sorry, 0.05 s of t plus 10. And then taking the limit as h goes to 0, we get a similar differential equation. S prime of t is 0.05 s plus 10. And again, what's nice is we can interpret this in terms of our model. This 0.05 s of t, that is the savings growth, thing without us forcing to put the money in, and this 10 comes from our contributions. It's the money that you contribute. Think like putting money in a retirement account. Okay, and as I promised, I will not resolve this equation because this is an integrating factors question. Solution. So this is of the form s prime of t minus 0.05 s of t equals 10. So what you do, you multiply. This is the e to the at problem. E to the minus 0.05t And again, you can either see the notes or just compare it with the video on the falling ball. So see notes. And then you get S of t is minus 200 plus c e to the 0.05t. Again, which seems negative, but it's actually positive, because if then you use s of 0 equals 100, then you can see the notes, you get c equals 300. So s of t is 300 e to the 0.05t minus 200. Like 300 as in, this is Sparta. This is differential equations. Okay, but again, that is not the answer to our question. The answer to our question is, well, we need to figure out when this is 250. So I think step 3, S of t equals 250. Again, I will not do the whole thing, but 300 e to the 0.05t minus 200 equals 250. Again, you use ln and solve for t. And in the end, and that's the t, you get t is ln of 1.5 over 0.05. So in our previous video, we saw that in order for money to reach $250, we had to wait 18 years. The question is, how much do we have to wait? With our extra contribution, only 8 years. So certainly contributing the $10 a year accelerates it, but not by much. And in fact, not to be pessimistic, but in those 8 years, you contributed. How much did you contribute? Well, we at the $100, and then every year you contribute $10. So you actually contributed $180. So the actual gain is just $70. Which is 250 minus 180, which is $70. Okay, so once again, I'm not a financial advisor. This is not financial advice, but maybe not the fastest way of your money to grow, but at least the safest, right? That's important. And now we'll move on to happier examples.